All right. Um, so a critical value was something that I identified when we talked about confidence level and significance level. So let me just talk just a little bit more about that. And again, um, just specifically, talk about how you find it. Okay. So a critical value is a z-score that delineates the border between the confidence level and the significance level for a statistics scenario. So a critical value, can be a z-score if we're talking about a left-tailed or a right-tailed distribution, or a z alpha 2 score if we're talking about a two-tailed distribution. Now, later, we're going to be talking about other kinds of distributions. So when we have a normal distribution, this is when you're going to see z-scores. But if we use a student's t-distribution, then we're going to see t-scores. And when we use a chi-square distribution, we're going to see chi-squared scores. Okay. And so those are just all going to be values that delineate a border between one area and another area, usually a confidence level and a significance level. Um, so, right now we've got a Z critical value, but very soon we're going to have a T critical value. And later we'll have a chi-squared critical value, an F critical value, and even an R critical value. All right, and what this picture is meant to represent, is here we've got a typical, normal distribution. We've got a typical normal distribution here, and notice that we've got a confidence level, which is the area on this side, and that's separated by this border line. And on the other side of that border line, we have the significance level. So that's this area here. And the value that defines the location of where that border line is the critical value. And so this would be where our Z critical value is located. So typically you're going to calculate this critical value, where the border is between the confidence level and the significance level, by taking this area and converting it into a value on the number line. And to do that conversion, this is where you use an inverse distribution function. Because an inverse distribution function makes you go in this direction. If you were starting from some value and you wanted to calculate an area, that's where you would use some kind of CDF function for that. But because we're interested in going in this direction to get this critical value so that we'll know exactly where the boundary is between these two areas, the confidence level and the significance level, we need to use an inverse distribution function. So in this example, it's find the critical value corresponding to a specific confidence level. So find the critical value, Z alpha 2, corresponding to a 90% confidence level. Right, so right off the bat, I know that this is a two-tailed distribution. How do I know that this is a two-tailed distribution? I know that because we're being tasked with finding Z alpha 2. And Z alpha 2 Remember that alpha represents the significance level. And when the significance level is divided into halves, when it's divided by 2, this means we're taking the significance level and we're separating it into 2 tails, one on the left and the other on the right. So by seeing this subscript here, that tells us we're dealing with a 2-tailed distribution. This one here in the example, this one would be an example of a right-tailed distribution. And the reason why it's right-tailed is because the significance level is on the right. So the significance level here is on the right-hand side. It's on the right tail. It's on the right edge. Okay. So, it just always helps to draw a picture. So I'm just going to draw a really quick sketch of a normal distribution. And it's 2-tailed. So that means I'm going to have 2 boundaries. And those boundaries are defined by these 2 critical values. So we're going to have a positive Z critical value and a negative Z critical value. Coincidentally, this will be the positive Z alpha 2 score, and this will be the negative Z alpha 2 score. But this particular Z alpha 2 score is considered a critical value because it's the boundary between the confidence level in the middle, which is 90%. That's what was given. And in order for the total area under the curve to add up to 1, we have to remember the confidence level plus the significance level is equal to 1.0. So if the confidence level is 0.9, and to solve this little algebra equation, we can subtract 0.9 from both sides. What we're left with is that the significance level is going to be 0.1. Remember, this is 2-tailed. So we have to take this significance level and split it into 2 equal pieces. So 0.1 divided by 2 is going to be 0.05. So 0.05 is the area in one tail, and 0.05 is the area in the other tail. All right, and now we can use inverse norm. There's a myriad of different ways you can do it. Often you're going to be using this Z-score, this Z critical value, in a calculation somewhere, like we just did with calculating margin of error. So it helps to have a positive Z-score. And so where you're going to have a positive Z-score is going to be related to the right tail, of this distribution. So if I was going to do one based off of this picture, using the Texas Instruments, maybe have an area of 0.05 with a mean of 0 and a standard deviation of 1, and I want the area to the right. And with the NumWorks calculator, we have a mean of 0, standard deviation of 1. I want the area to the right, and the area is going to be 0.05. And when I hit enter, it'll just give me the value. And that value is going to be plus and minus 1.645. So let's maybe take this opportunity to kind of just look at all the different ways we would get 1.645. So if we were using the Texas Instruments calculator, let me go to the distributions functions, go down to inverse norm, and I have an area of 0.05. Okay, mean of 0, standard deviation of 1, tail on the right. And let me paste and give an answer. There's our 1.645. Now, if instead of calculating the z-score on the right, if I calculate the z-score on the left, it's going to be the same number, but it's going to be negative. Okay, so let me show you that. So let me do inverse norm. We're going to put in the same area, but we want the area to be on the left. Now when I put paste and answer, notice it's the exact same number, it's just negative. And the reasons why it's negative is because we were calculating the area from the left. So the related z-score is going to be a negative value. The center of this, is 0. Okay, so you're going to have negative values in this direction and positive values in that direction. Positive z values. Now, if we wanted to use center, okay, then we have to use this center confidence level area of 0.9. So here we are, second vars key, that gets us to the distribution menu, inverse norm, and now an area of 0.9. And this time I'm going to put center, come down and hit paste. And you see, because I'm using an area of 0.9, which is the area in the middle, it's giving me the negative z-score and it's giving me the positive z-score, both at the same time. So, I mean, if you know what you're doing, you can get the same value using left, center, or right. Now, again, I want to caution you, if you're using an older calculator, like the TI-83, and if you go to the distribution menu and you choose inverse norm right off the bat, it doesn't allow you to choose left, center, or right. The native inverse norm function on the older Texas Instruments calculators only calculates area from the left, only from the left. So, you'd put in the same values separated by commas like that, but you can't put left, center, or right now. And so you hit enter and notice it's giving you the z-score as though it was calculating the left tail. It's giving you this negative z-score. Okay. But this is particularly the reason why I decided to write my own inverse norm function as a program. So if you click on programs, and I've installed this onto your calculator, there's an inverse N83. And when you run that, you put in your area. So I'm going to put 0.05. Actually, let me put in 0.9. We'll do center, right? We'll do a center calculation. So a mean of 0, standard deviation of 1. And we want to use the area in the center with an area of 0.9. So now it's telling us that we have a positive and negative z-critical score of 1.6448536. Positive and negative. If we use this again, and this time I put an area of 0.05, area or mean of 0, standard deviation of 1, and I put the right tail, that should give me a positive z-score now, because now we're putting in an area of 0.05 with the tail on the right. And you see now it's a positive Z critical score of 1.645. Okay. And on the NumWorks calculator, you know, last but not least, um, if we go to the distributions app, click OK, we go down to the normal distribution, put in a mean of 0, standard deviation of 1, and area from the left, we put in an area of 0.05. Okay, so now that we're going to have an area to the left with an area of 0.05, we're going to expect this z-score to be a negative 1.6448 something or other, right? There, and see it shows it. If I change the area to be to the right, and I put an area of 0.05, see now it's giving me a positive 1.645. And then if I change the area to be the area in between, in the middle, and I come over here and I put 0.9 now because that's our confidence level. Our confidence level is the area in the middle. It's giving me negative 1.645 and positive 1.645. All right. So, whenever you need to convert an area into a critical value, you need to use an inverse distribution function. And I've just shown you like all of the inverse distribution functions on old and current calculators, um, and how you can use them fully. Okay, so this was the right time to kind of dive into that a little bit more. All right, so that concludes this little video. Let me know if you have any questions.